Hi everyone, my name is Mike, and this is some work I presented at the Computational Intelligence in Games conference in Maastricht in 2018. It's about some work we did setting up the kind of first build of the new version of Angelina, and it was done with Simon Colton and also Azalea Rad at MPI-SWS. So Angelina, if you're not familiar, is my automated game design system. I've been working on it on and off for the last 8 years or so, and the latest version, which was built over the course of the last 18 months, is the one I've been talking about lots lately, and it looks a bit like this. You can actually play all of Angelina's old games, some of its new ones on itch as well, if you're interested in that. But the problem I want to talk to you about today is something which came up while I was building the new version, which is this problem of what you actually know about a game when you're building it. So when you're halfway through building it, you don't have any levels, but you have an idea for what the game's rules are. But what does the rules tell you in the absence of any other content? What can we find out about this game? So there's two motivations for this work. One is that the new version of Angelina, as you'll be familiar if you've watched any of my other talks, is much slower than all previous builds. So this is sort of counterintuitive. Most AI systems at this conference that I'm speaking at are being made to go faster. Like all these deep learning systems need to be optimized, they need to be given more compute. But Angelina is going to work slowly. And this is going to be true really regardless of what we want to achieve, because there's loads of reasons why we want Angelina to work more slowly. It means that it can work with humans, it means that it can have playtesters, create more interest, people can watch it make games. And so even if Angelina does a lot of work, we want it to take its time to make this game. We want it to put lots of effort in and make a higher quality game. So that means that it might take days or weeks. And what that also means is that a bad idea at any point in the design process needs to be gotten rid of as soon as possible. Because the quicker we get rid of a bad idea, the less of an impact it has wasting time in the process. Which means that if we're at this conceptual stage where we're still thinking about a game design, where we've just maybe got a rule set right at the top of this task list, then if we can get rid of it at the rule set generation phase, we're going to save ourselves loads of level design time that would have been wasted finding out that this game wasn't any good. So that's obviously a great practical reason for this work. There's also kind of a philosophical reason as well, and that's because being a good game designer does involve being able to assess ideas and be able to talk about them with other people. So this is Rami of Vlambeer, and he's given several talks in the past where he's gotten members of the audience to just stand up and pitch him their game, and then he gives feedback on their pitches. And this is the kind of thing designers are very good at doing. But it's also things that just humans are very good at doing. Everyone's got an opinion on your game design. And we share them with our friends, with people that we work with in teams, people that we're mentoring, as well as using it on our own game designs when we're doing work. And it's an important way in which we convey the kind of designer we are to other people. So we can demonstrate how good of a designer we are or what our personal style or opinion is by talking about our feelings and intuitions about a game design. And I've put the word performing on this slide because to some extent, as you know, that's what Angelina is doing. It's not just enough for Angelina to design good games. It has to be seen to be performing the acts of a good game designer. So that's the motivation. How do you actually know if a rule set for a game is any good? And the way that I put this when I was first thinking about this idea was if I showed you the rules for chess and you'd never played it before and you'd never even seen a chessboard, would you know that chess was good or interesting or had curious qualities? And how would you know that if you were just looking at the rules and you didn't know what chess it was actually like to play? So the way we answer this question is by building something called an action chain. So action chains are kind of like solutions to levels, but for levels that don't exist. And instead, they're sort of abstract collections of actions that you do, which lead you to either winning or losing the game. So on the top here, you have an abstract action chain that solves a particular game where you have to find a key and then get to a locked door. And it doesn't talk about the specific things you have to do. Instead, it talks about the general actions that you're going to go through. So you're going to first move the player to the key to pick it up. Then you're going to move the player to the locked door, and then you're going to win the game. A solution to a particular level is normally a very precise collection of moves. You know, we could switch off. I haven't even said what this game is for at the bottom. It doesn't matter. You don't need to know what game it's for. All you need to know is that if you press these arrow keys in this order, you'll complete this particular level. So the difference between a solution and an action chain is very general, and it talks in general abstract ideas. So we're going to talk about how we build action chains over the next few slides. I'm going to give you an example. And the example we're going to use is a game called Soccer Band, which you may be familiar with. If you're not, it's really not important. It's just that if you are, these examples might be a bit easier to follow. And I'm also going to show you snippets of code from Angelina's design language. It's not really important you understand the design language. If you're interested, there's more details in the actual paper, but it's fairly straightforward. So for instance, these 2 lines of code say that one of the ways in which you can win this game is if all of the crate objects are on a goal object. And if you know Soccer Band, this is one of the win conditions of Soccer Band. So the way we build action chains is we go through the game's rule set, and for each one of these end conditions, whether it's a win or a loss, we create a new action chain. And it just has one node in that says win or loss, and at the bottom we're going to write the trigger for this end condition. So in this case, all crates are on goals. And this trigger becomes our new objective. We need to find a way of causing this trigger to happen. And we're going to do it by searching through the code base for another kind of rule. But what rule do we want to search for? Well, to find that out, Angelina uses a lookup table that we've prepared for it that tells it, for the general case of a rule, what other things cause progress towards this rule. So the general form of all crates on goals is all x's on y's. And we've told Angelina that one of the ways to progress this is if you can move x, because if you can move x, you can move them into position so that they're over y. Another way would be if another kind of object pushed x, because then you could have a way of displacing x in another manner. And each of these will have a different requirement to complete the action chain, and we're going to see that in a second. But Angelina tests each one of these in order. So we're only going to look at one, but Angelina will perform this process for every single one of these to see what different ways there are to achieve this sub-goal of all crates on goals. So we're going to use this one for now because this is actually in Soccer Band. So we're going to be looking through the code base for something that pushes crates. So some kind of Z that pushes X, and X in our case is a crate. So we look through the code base and we see like rules that say when you press arrow keys, the player moves or whatever. And then we find this rule that says when a player collides with a crate, the player pushes the crate. And we're searching for this sub-goal, this progress condition that is going to be in the body of one of these rules. And in this case, we found one because we were looking for push something crate, and we found it, and the something was player. And what that means is that we can now add a new node to our action chain, which looks like this. And this node is pushing crates, which achieves our sub-goal of all crates on goals. And this rule of pushing crates has a new trigger, which becomes our next sub-goal. So I've written this at the bottom of this action chain node, which says collide player crate. So this is the new thing that we're looking to prove, and Angelina will go back to its lookup table and look for things that cause progress towards colliding x's with y's. And we're going to repeat this process basically until we reach an action which is caused not by some arbitrary trigger, but by player input. So in the case of Soccer Band, it's actually quite a short action chain. The player moves, the player is used to push crates, and you win when all crates are on goals. So there's only 3 steps, but crucially, moving the player is something which is initiated by the player by pressing arrow keys. And at that point, the action chain is done, and we can go and look for other action chains. Obviously, a single win condition can have many routes that lead to it. That's not a problem. We'll just produce multiple action chains. And there are different things you can infer about a game based on how many action chains it has or how long they are. And as I mentioned previously, chains can also be for lose conditions. So in this case, if you run out of cakes, you lose, monsters eat cakes. There's a slight small detail here, which is that even a loss action chain is still initiated by player action. And this is not an important detail particularly, but it is a kind of an idiosyncrasy of Angelina's engine. Because it's a turn-based engine, all action in the game is technically initiated by the player, because monsters won't move until the player has moved. But this is a very minor detail, and it's not really like a property of action chains. It's more of an implementational detail for Angelina. So there are lots of different ways that you can use action chains that I don't have time to go into here in terms of what they tell you about a game. But the way Angelina currently uses them is that it requires every game to have one winning action chain and one losing action chain before it uses the rule set. Now, this isn't a hard requirement. There are lots of games that don't have losing action chains. This is A Good Snowman is Hard to Build by Alan Hazelden and Ben Davis. And this doesn't have a way to lose. You can always undo the last step you made. It's a puzzle game. And that's not a problem. Like, it's not necessary to have a game that can always be lost. So this also isn't a general rule, is what I've written here. And what I mean by that is that we want Angelina to have flexibility over this in the future. So in the future, Angelina might be able to decide that it wants to play games that don't have a lose condition, or it wants to have games that have many different ways to win, that kind of thing. It's really important to point out at this point that action chains don't actually tell us a lot about a game. They're a necessary property that a game needs to have to be playable, so they guarantee that there is some logical way to win a game. But they don't tell you whether that way is good. They don't tell you whether it's easy to design. It might actually be very hard to design levels that have these paths in them. It just tells you that these paths exist. And this can kind of sound like kind of a downer, maybe. And you might wonder, like, if action chains are so basic and they don't really give us that much information, how useful are they? Well, to give you an idea, we did a little design space experiment. We sampled 50,000 games from Angelina's design space, totally at random. And what I did was I applied the old filtering that we used to use, which really just looked for very obvious contradictions. For instance, if the game has the same win and loss condition, or if there are some rule constructions that are just strictly contradictory. And that kind of filtering removes about 10% of the games that we generated. If you apply the requirement that all of these games need to have one winning action chain and one losing action chain, you filter out 99.5% of games. Now, when we put this paper in for review, some of the reviewers questioned whether this was a good idea or not, and they were worried that maybe the remaining 0.5% of games would be very samey or similar, or we were somehow throwing out games that were maybe good. The reason why we don't need to worry about this, or at least I don't think we do, is that in the past, a lot of automated game design systems, and I'm mostly talking about Angelina here, but I think it's true of some of the other systems out there, implicitly did this kind of filtering just by never letting those games get generated in the first place. But the way it did that was by aggressively shrinking its design space. So in the very first version of Angelina, which what these screenshots are from, we had these templates for rules that we would slot object types into. And they were basically designed so that any rule or any collection of rules would lead to a playable game. It didn't necessarily lead to a good game, but the games were always playable, and really Angelina's only job was to find out which ones were more interesting than others. So what we were doing was, in the design of Angelina, in the structure of the system and the grammars that we use, we were already putting in this kind of filtering super aggressively so that Angelina couldn't put too many feet wrong. And to give you just a visual representation of what I mean by this, Angelina's old design space was like this tiny, tight little circle drawn very cautiously around just a few good aspects of this massive game design space. And all we've done here with Angelina is to massively increase the scope of this design space. So it includes a lot of games that we don't want, but it also includes a lot more good games that we wouldn't be able to discover otherwise. And all the action chain filtering does is it removes the games that we obviously don't want. It doesn't remove all of them, but this new, larger design space has a lot more stuff that we don't want to see in it. And action chain filtering allows us to get rid of things that we know 100% we don't want to get rid of. So every game filtered out in that 99.5% would never have been finished by Angelina. Angelina would have thrown it out at some point in the future. It's just that we allowed it to realize that earlier on. So that was action chains. And action chains seemed really useful, and they were really helping Angelina get through the early part of its design phase kind of faster. But then I began to look at what these action chains were telling us, and I realized that they were kind of containing extra information. So when you just look at the list of rules in one of Angelina's games, they're actually really hard to follow. They're just a jumble of causal statements and if-thens, whereas action chains are really neat. They tell you which parts of the rule set are useful and which parts contribute to the winning paths through the game, which parts contribute to the losing paths. And by doing that, they also tell you which rules are really important and which rules the game kind of depends on to make it playable. And what that also means is that they contain extra design knowledge kind of hidden inside. So in Soccerban, the win condition, all crates on goals, tells us implicitly that the number of crates in the game must be greater than or equal to the number of goals. And if this seems like an obvious constraint, this almost doesn't seem worth talking about, because it is so obvious you can hardly imagine Soccerban any other way. But actually, it's not obvious to Angelina, and this allows us to use action chains to have a kind of logical check on the ways in which the player wins the game and find things that must be true. So what we do is we've built this additional lookup table that has constraints in it that are tied to general rule patterns. And as Angelina builds these action chains, it checks to see if any constraints are implied by this. And it does a bit of extra deduction on top of that. So this is a very simple constraint that's only implied by one rule. But there are also more complex constraints that are implied by multiple rules. So for instance, if you need to score 5 points and you win a point every time you eat a cake, there must be at least 5 cakes in a level to be completable. So Angelina can extract these constraints, and what it does is it puts them inside the game project file. So every game Angelina designs has this big project associated with it, and these constraints stay with the project for the duration of its design. So when it's finished designing the rules, it remembers what these constraints are. And what that means is that we can use the constraints later on. So when we're doing level design, which uses an evolutionary process, we can use these constraints to filter the randomly generated populations for our evolutionary systems. So what that means is that when we're generating Soccerban levels, for instance, we only accept levels into our population if they have the right number of crates. And this filtering seems like it might not have too much of an impact because the constraints seem so obvious, but it actually has a massive impact. So we did another test. We generated 10 different game rule sets, and for each one we generated 50,000 levels and then filtered based on the level constraints inferred from the action chains. And what we found was that we filtered out about 3/4 of the randomly generated levels, which when you think about it is not that surprising. We would expect it to be that high. And you'll notice I've got two types of filtering here. The reason for that is if you imagine a game in which you need to adventure through a maze to reach an exit and you have to avoid monsters, it's not necessary that there are monsters in every level. And in fact, in a tutorial level, you might not want there to be monsters. So strict filtering says every level produced by this game must have all of the winning constraints and all of the losing constraints applied to it. Whereas more lenient filtering says that only the constraints that relate to winning must apply. So it would not require there to be monsters in the game, but it would require there to be at least one key for the locked door, for instance. And you can see that this had a big impact on the amount of levels that actually got fed into the evolutionary system. And what that means is that has a knock-on effect which raises the quality of the populations that are being evolved. And so we hypothesized that this would have an impact on the evolutionary system, and it did. And I'm not going to go too deeply into this graph, because that's mostly, that's what a lot of the paper spends its time talking about. But the bottom line is that by constraining the populations used for evolution, what we found is that you converge on higher quality solutions faster, which is really good news for Angelina because it really wants to do these fast iterations of level design so that it can go back and try different things. And we also looked at things like just constraining the initial population or constraining the process as it goes along as well, and that has a different impact. But basically, filtering levels based on these level constraints has a big impact, and this is great. This is what we hope to see. And what it means is that Angelina analyzes its rule sets at the beginning of the design process, and that knowledge that it derives from that analysis is used to improve the rest of its design process, which is a really cool little detail. So where are we going from here? Well, One thing we'd like to do is be able to build action chains that are sensitive to more complex game logic. So, for instance, if you have a rule that says when players touch monsters, they die, and this is a very simple rule, and maybe in your game you need to kill all the monsters to win, and so this rule will be part of the action chain. But now if we modify that rule, so it actually says that when you overlap with a monster, the monster is killed, but also it spawns a new monster, then this would actually make the game unsolvable because you'll never be able to destroy all of the monsters. It doesn't entirely make it unsolvable, actually. If there is only one monster, Angelina's engine will probably let you win this game, actually, I think. I'm not sure about order of operations. But basically, you cannot win in the general case. And action chains should be able to tell us this. So we want action chains to be more sensitive to this kind of thing and also more sensitive to branching. So there are going to be cases where action chains have to branch and essentially prove like a conjunction of triggers. And we needed to make sure that it understands that if something happens in one branch that is contradicting something that happens in another branch, then that action chain can't be proven. We'd also like it to be able to intuit high-level design ideas. So when you first think about Sokoban, Sokoban seems to be just this primitive game about pushing crates. Like, that's how Angelina sees it. It sees it as a game where you perform single actions like push crate or move player. But game designers think about Sokoban differently. You might start to think about Sokoban as a game where you're clearing paths for crates. Instead of, pushing crates isn't important. What's important is clearing a safe path. And then later on, you might start thinking not about the physical space at all, but about the spaces that don't have anything in them, and think about managing empty space. And when you talk to designers or you talk to players who have played a game a lot, like if you've ever really gotten into a game, you'll have developed this kind of higher level idea about what the game is. And this sort of knowledge is really interesting. And it's not just interesting to analyze a game, it's interesting before you've even started designing a game often. Often this high level idea guides your level design, it guides the way you add to the rule set. And I think this is the kind of thing we'd really like to be able to do with Angelina, and have it figure out that this rule set is not just about primitive actions, it's about higher level macro ideas, sequences of actions, strategies, tactics, things like that, and how this will affect the way it designs levels. And on that note about higher level design knowledge, I just wanted to plug a paper that was recently presented at FTG, and I believe it won a Best Paper Award there. And it uses kind of a similar approach to action chains, but it does so much more, and it's really influenced my work in this area about designing tutorials for games. It's a really fun paper. You should read it. It's very approachable, very understandable, and I'm really excited by where that work's going to go as well. Another thing that we'd like to do is automate the reasoning process. So earlier on, I talked about lookup tables that tell Angelina how to make progress towards a certain goal, and also lookup tables that tell Angelina what constraints apply to certain rules. Now, if you work in game AI, your worry about that is probably that is a hell of a lot of information to create by hand, which it is. And the other problem from a computational creativity perspective is that it is a lot of input provided by a human being, which is a big deal for Angelina. It's a big deal for me. So what we want is to give the system the power to come up with these things itself. So when it sees a rule, it can do some tests and experiments and figure out what is implied by this rule, what things cause progress towards this rule, and it'll be able to create these lookup tables for itself, hopefully. All right, thanks very much for listening. If you want to get in touch with me or with Angelina, we are both on Twitter. Angelina should be tweeting and streaming again soon. Sorry, it sort of fell apart over the summer. I've been working on other things. One of those exciting things is that I will be moving soon to Queen Mary. I won't actually be moving to Queen Mary. I'll still be in Germany for a little bit. But I've recently won a Royal Academy of Engineering Fellowship, which is super exciting. That will give me 5 years of funding to work on Angelina and lots of related ideas to it, so I'm super excited about that. And also, I've got a book coming out. So Tony Veal and I have written a book about Twitter bots. Tony's written this great central section about the whole book. It's really massive, and it's sort of a guide to building computationally creative Twitter bots. And I've written a few chapters about the history of generative software and generative ideas, and the history of the Twitterbot community as well. There's some interviews with Twitterbot makers. If you like my stuff, I really think you'll like the book, and it's coming out in September. Thanks very much for listening, and yeah, that's all I've got.